Hello everyone, welcome back. In the previous two lectures, we discovered something very important. Real amplification fundamentally requires additional power source and some form of nonlinearity. But at the same time, we also want our amplifiers to behave linearly. So now the biggest question becomes, how do we make a nonlinear device behave like a linear one? And the answer to that question leads us directly to one of the most important concepts in analog design, and that is small signal analysis. Today, we will derive the real origin of small signal analysis completely from scratch. Okay, let's begin. So let us quickly recap where we are standing. Previously, we learned that there is nothing truly active in physical reality. Every real device dissipates power, and purely linear system cannot transfer DC power into signal power. So we were forced to use nonlinear device, but nonlinear systems create a new problem. They are difficult to analyze. We can't use our linear circuit theory, and also it creates harmonics. Okay, so we need linear system, so we need linearity. So today we will develop a framework to linearize non-linear element. So first, we'll connect an unknown nonlinear element with a linear resistor and create a load line framework. Then we'll study how the operating point moves when a signal is added. After that, we'll discover why normal analysis gets stuck, right? And finally, we'll introduce some magical things, introduce our magical mathematical tool, Taylor series. And using Taylor series, we will derive the origin uh, of the incremental model and small signal approximation. Then we'll apply this framework to voltage source, current source, and finally a diode. And at the end, we'll answer a very important practical question: how small is actually small in small signal analysis? Okay. Uh, here is the whole thing. You can read all those 9 points. Okay. Now let's go to slide 3, our framework for linearizing a non-linear element. Suppose we have an unknown non-linear device. This is our non-linear device IN. This is the current through this non-linear element NLE, and this is the voltage across the NLE. Okay, suppose we have an unknown nonlinear device and we don't know its analytical equation. We only know that its current and voltage relationship is nonlinear. Now to analyze it, we connect it with a linear resistor. Why? Because the resistor gives us something very powerful. Okay, uh, a linear equation from KVL. The resistor acts like a bridge between the unknown nonlinear world and the known linear world. Okay, now by plotting, we will have to plotting the nonlinear IV curve, right? So number one, connect with LE and simulate. Find out IN versus VN graph. So we'll find out this IN versus VN graph. Okay. And by plotting this nonlinear IV curve and the resistor load line, their intersection gives us the operating point, also called the Q point or quotient point. Okay, the operating point will become the center of our future small signal analysis. So number two, draw load line by using KVL for for linear element and find Q point or your operating point. Number three, add swinging effect to Vn and In as Vn is swinging and analysis. We'll add some swinging effect here. This is only DC bias. I will add a small signal across it. Okay, on the top of this Vn. Now going to slide 4, let's see. So first, let us consider only the DC bias condition. No signal swing yet. The nonlinear device follows some unknown relation. I in equals some f of Vn, right? In is equal to some f of Vn. And we don't know the analytical relation. Okay. Now we may not know the equation, but we can still obtain the curve experimentally, numerically, or through simulator. You can use your favorite simulator. Okay, since the resistor is linear, we can directly apply KVL, and because the resistor and nonlinear element are in series, the same current flows through both. Okay, the intersection of this two relation gives us the operating point. This operating point is extremely important because later we will locally linearize the nonlinear device around this operating point. Now, this is V in, this is V in. There is a voltage drop across this nonlinear element which is Vn. Now, what is this voltage across this resistance, this point? This is nothing but V in minus Vn. After Vn, after drop Vn, this voltage will be V in minus Vn, and this is ground. So, what is the current? From Ohm's law, we can say In is equal to V in minus Vn minus 0 divided by R. I don't write the 0. Okay. Now In times R is equal to V in minus Vn. Now V in minus Vn is equal to In times R. It means Vn plus In R is equal to V in. Now we'll divide it by V in and we in both side, and we get Vn by V in plus In by V in by R is equal to 1, which is exactly looks like a mathematical formula or a mathematical equation of straight line, which is x by a plus y by b is equal to 1. Okay, let's see the curve. This is the curve which is x by a plus y by v is equal to 1. This is the case 1 biasing picture. Okay, this is the curve. So this is the linear element, the resistor, the from KVL, and this is the non-linear element, and this is IN and this is VN. So this is the case 1 biasing picture. Okay, so now, can we find a relation between IN and VN? This IN and VN without including the V in. So we don't want to including the V in, but we want to find the relation between the IN and VN as we don't know the analytical function. Okay, let's see. So we are focusing on only case 1, not case 2. So now we'll we'll get our focus into case 2. Okay, let V in is swinging. Okay, let V in is swinging due to presence of a small signal riding on top of the bias. So this is case 2. So this line which was V in 0, it will be V in plus del V in. Okay, so this thing is del V in plus del V in. This del V in is due to the swing of the signal. Okay, so this load line is swinging up and down, up and down. Okay, nice. Now, so after this, V in is not V in now. V in is V in plus del V in, and IN is not IN now. It is IN plus del IN. Okay, so this current is generated due to the small signal. Now, so case 1, we can see In is equal to V in minus Vn by R, which is equation 1, and case 2, In plus del In is equal to what? This V in is not V in now, V in plus del V in from that picture minus Vn plus del Vn. That means this is not Vn now. Okay, this Q point, this operating point IN VN, this is not VN now, this is VN plus del VN, and this is IN plus del IN. This small portion is del IN, this small portion is del VN. So VN plus del VN by R. Okay, so this is the equation 2. Now, so in this slide, we are adding the small signal. Okay, so as the input swing, both voltage and current of the nonlinear device also swing around the operating point. That's the thing. And now we ask a very important question: can we derive a relation between incremental voltage and incremental current without explicitly involving the input source? Because if we can, then we can model the nonlinear device independently using only local information around the operating point. That's a very important thing. Okay, let's see. uh, okay, so by subtracting 1 from 2, we find the incremental current as del In del V in plus del Vn by R. So now the question, are we stuck? Or we came back to the same problem where del V in is incorporated? Let's see, this is the del V in, it is, and let's see the first equation. This was the first equation. In is equal to V in minus Vn by R. Okay, now In is equal to del V in, this will be minus, sorry for the mistake, this will be minus del V in del V in minus del Vn by R. So this will be minus, and we are getting the same equation as case 1. So no improvement, okay? And we came back to the same problem where del V in is incorporated. So the thing is, now we hit a major problem. The nonlinear relation still contains the original nonlinear function, and the input signal variation still appears inside the equation. So we are stuck again. That's the truth. We need a method to isolate delta I and delta V without carrying the full nonlinear expression everywhere. And this is exactly where mathematics saves us. To escape from this problem, we need Taylor series. So we need a relation between del In and del Vn without incorporating that del V in. To solve this problem, we have to recall our Taylor series. That's the must thing. Okay, let's see. Uh, so uh, let's we are literally introducing you the Taylor series. Okay, Taylor series is one of the most powerful tools in engineering mathematics. Its beauty is simple. It is simply beautiful. Even if a function is non-linear globally, locally it may look almost linear. Taylor series allows us to approximate a complicated nonlinear function around a particular operating point. In other words, instead of analyzing the full nonlinear mountain, we zoom into a tiny region where the curve almost behaves like a straight line. That tiny local approximation becomes the foundation of small signal analysis. Let's see. So this is the Taylor's theorem. The Taylor's theorem is stated that if a plus h be a function of the variable h such that it can be expanded in ascending powers of h, and this expansion be differentiable any number of times, means it is smooth at a. I'm I'm telling it is smooth. What is mean by smooth? It is mean that the expansion be differentiable any number of times at that point. Then f of a plus h is equal to f of a plus h f prime a. This f prime means one time differentiation of the function h at point a. H square by 2 factorial f double prime a. This f double prime a means differentiating that function of variable h, okay, two times at that point a. That's the thing, at that point a. Okay, now if a is equal to 0, it's nothing but Maclaurin series. If a is not equal to 0, it Taylor series. Okay, now the thing is, A is our approximation point or base point or DC operating point. Okay, you can say your bias, your Q point, anything. H is variable, your small signal, your incremental signal. Okay, now we will see something. Okay, now we will see from uh, Desmos our Taylor series, how our Taylor series actually work. Okay, let's see. So this is the Taylor. This is the function of e to the power x. This is the function. Sorry, this is the function of ln x, not e to the power x. So this is the function of ln x, and now we want to approximate it. Okay, with this red function. So the blue function is the actual function ln x, and this red one is approximated function. And approximated start from where? Start from this approximation center or approximation point. And what does this number n means? This n means the degree. Okay, uh, the more degree, the more accuracy. Okay, so if I make this number greater, we can see it's better on accuracy, right? And if we swap this the value of approximation or the base point a, this point will move further. Okay, so I'll give the value a is equal to 5. Let's see what happened. Yes, this is on 5, right? And for this boundary to this boundary, from this to this red line and this blue line is same. this red function is, and this blue function is same. This red function is not mimic the blue function as a whole, but it it is localizing the mimic. Okay, it is mimicking, localizing from this boundary to this boundary. Okay, now let's see one thing. Let's increase the number n. Okay, yes, so the boundary increases, right? The accuracy increases. So this is the thing. If we so this is the approximation center. So this will be our bias point. This will be our operating point. Okay, where we can bias our transistor, where we can bias our device. Okay, so this is the thing. We'll also see that for a sine function. Okay, let's see for a sine function. So this is a function f of x is equal to sine x. This red one is the function, and by using Taylor series, I want to mimic the red one with this what is this color, purple, with this purple one, right? But this is not mimic the whole. This is from this boundary, this limit to this limit only. Okay, if I decrease this thing, it will decrease. Okay, decrease the accuracy. Now if I set this n is equal to 1, okay, then what happens? Let's see. If I set n is equal to 1, then it this purple line is mimicking this sine graph with a straight line. Okay, only with a straight line. So this is linearizing this thing. Okay, only with a straight line if n is equal to 1. So basically the thing is, we will omit all of the higher order derivatives, and only the derivatives with n is equal to 1, we will collect only this one, and uh, um, we'll omit all of the higher order derivatives. Okay, now for n is equal to 0, what happens? Let's see. Nothing. Okay, for n is equal to 1, let's see, n is equal to 5, and let's change our approximation point. This approximation point was set at 0, so the approximation start from 0. Okay, let this approximation point to 6. Okay, so this will be start from here. Okay, 6. Yes, let's see that this is approximation is start from here, but we don't want this non-linear thing. We don't want this non-linear thing. So we don't want n is equal to 5. We want n is equal to 1, but we want to approximate. Okay. Yes, we can approximate this portion from this to this. Okay, we can approximate only this as a linear. So the whole thing is non-linear, but this thing is linear. Okay, I think you all understood that the Taylor series and the Taylor series approximation. Okay, uh, now we'll go forward. We'll go back to our lecture. Okay, okay. So this was the Taylor series. Okay. So when I am telling the n is equal to 0, it is only f of a. When I am calling n is equal to 1, this is f prime a, or f of 1a. Only this term. N is equal to 2, this term and this term. A double differentiation. N is equal to 3, third time differentiation. Okay. So we want only this one, and we will omit all of this higher order term. Okay, and from that the true origin of small signal model will come. Okay, let's see. Now we'll apply Taylor expansion to our nonlinear current voltage relationship. Okay, the total current now be written as the DC operating current plus incremental term. The first, so this is V in, this is plus del V in with the small signal, and this is IN from this V in, and this is del IN from this del V in. Okay, and as this current IN plus del IN goes through this nonlinear element, so there will be a voltage drop, and this Vn is dropped due to this IN, and this del Vn dropped due to this del In. Now, so this was the curve, okay. So assume that a small signal is riding over a DC bias operating point or your Q point. So let In is a function of Vn. We already know that. So okay. So now In plus del In is will be a function of Vn plus del Vn. Okay. So this is equation 2. Now, uh, now In plus del In is equal to f of Vn plus del Vn. So In plus del In, we can write it. This is A, our Vn, and this is H. So f of A plus H, f of A plus H dou f by dou Vn. Okay. So this is the partial differentiation we can we can write with I write partial differentiation because sometimes our I will not be a function of one voltage. Suppose ID is a function of VGS and VDS. Okay, suppose our MOSFET in saturation but with channel length modulation. So ID is equal to half mu n Cx W by L VGS minus VTS whole square into 1 plus lambda VDS. So ID is not a function of VGS only. ID is not a SVF single variable function. It is a multi-variable function MVF. So ID is a function of VGS and VDS. So where we'll have to do a partial differentiation, not total differentiation. So I have to for generalizing the whole thing. I have to use some good good terms. Okay, so I use this dou. So del Vn dou f by dou Bn, and this differentiation should be done at what? Should be done at Vn, the operating point Vn. Okay, plus del Vn by 2 factorial dou square f dou Vn square means second time differentiation Vn plus del Vn by 3 factorial dot dot dot. That is the thing. Now by subtracting equation 1 from equation 2, we got what? We got some del In is equal to del Vn dou f by dou Vn at operating point Vn plus del Vn by 2 factorial dou square f by dou Vn square at operating point Vn plus del Vn by 3 factorial, and it's going on. So the thing is, now comes the key engineering assumption. If the signal swing is sufficiently small, higher order terms become negligible compared to the first order term. Okay, and suddenly our nonlinear device behaves approximately linear. So this is the part of the small signal model. So in small signal approximation, we can say let del V in is so small such that del Vn is also small enough such that the higher derivatives can be neglected with respect to the first derivative. Okay, so this derivative should be neglected with respect to this first derivative. Okay, why? Because this del Vn small. Why this del Vn small? Because del Vn is also small. So there is some constraint of small signal to be small. So how much small is small actually? Okay. Now the this thing. So we are assuming that del Vn is small. So del Vn is also small. So we already omit those higher order terms. So now we can write del In is equal to del Vn dou f by dou Vn around the operating point Vn, and we can write del Vn by del In is equal to 1 by dou f by dou Vn at that operating point Vn. So this is what? This is nothing but a resistor, right? 1 by 1 by dou f by dou Vn. So this is nothing but a resistor. So not a physical resistor, right? But it is a resistor. Okay. Okay, so now observe, we are observing something beautiful thing. Okay, some beautiful thing we observe. After neglecting higher order terms, we obtain a simple relation between delta current and delta voltage, right? The complicated nonlinear device now behaves like a linear element locally, and the slope of that local linear approximation becomes the incremental conductance or resistance. Okay, I am telling it, it is actually resistance, and this means small signals analysis is not magic. It is simply local linearization using first order Taylor approximation. That's the thing. Okay, so but now another practical question appears. and that question is how small is actually small. And we can, and this is our nonlinear element, this is our this is our register, this is in large signal and this is in small signal. We can we can tell that this r is nothing but 1 by dou f by dou vn around that operating point vn, but this is not a physical registers. Okay, so small signal approximation validation. So what is that? There is a maximum limit of del v in beyond which the incremental model is not valid anymore. We have to find out the constraint that how much small is actually small. Okay, so this is extremely important in practical analog design in real silicon. Okay, every nonlinear device has a valid small signal region. Outside that region, distortion increases, harmonics appear, and the linear model becomes inaccurate. So small signal analysis always comes with a validity constraint. You have to remember it. Okay, so now uh, we have to memorize this thing. Okay, incremental equivalent. So we got our incremental equivalent as 1 over slope of the this function is nothing but what, this dou f, this is dou I, actually dou I by dou vn. So this is the 1 over slope of the IV characteristics curve of that device, of that nonlinear element device around the operating point. Okay, your DC operating point dot DC you can run on cadence on your simulator, on your favorite simulator, any simulator. Okay, so this is your operating point, or you can do some hand calculation also to find that operating point. So that's the thing. So now now let us apply the framework to ideal sources. Okay, for an ideal voltage source the voltage never changes regardless of current. That means the IV curves has infinite slope and inverse slope becomes zero. Okay, so the incremental resistance becomes zero, which means an ideal voltage source behaves like a short circuit in small signal analysis. And that's why we always shorted our VDD in small signal analysis. Okay, we short our VDD. There is no VDD in small signal analysis. Then we tell how comes this generates from no power to power. Right? There is energy, there is free energy. So this is active device. Okay, so that's the thing. So now consider an ideal current source. It currents remain constant regardless of voltage. So its slope becomes zero and inverse slope becomes infinite. That means an ideal current source behaves like an open circuit in small signal analysis. This is the real origin of those famous small signal replacement rules. Okay, this is the real origin. Okay, now suppose this is some IDVD. Okay, now we apply our framework to a real nonlinear device, diode. Okay, so the diode equation is highly nonlinear. We can see here IDQ is equal to IS e to the power VDQ by VT. There is some VDQ by eta VT minus 1 Shockley's equation, but we are omitting those things by ideality factor is equal to 1, and VD is VD by VT. The ratio is much larger than 3, or VD is greater than 3 times of the thermal voltage VT, which is approximately 26 millivolt at as 27 degrees Celsius, or we can say 300 Kelvin, right? So this is the thing, and we can say IDQ plus del ID is equal to IS e to the power VDQ will be VDQ plus del VD by VT. Okay, now the thing is, can we find out this dou id by dou vd at vdq? Yes, we can find out. We can differentiate this equation id with respect to vd, and what will be that? E to the power x, the formula of e to the power mx. This is nothing but m e to the power mx. So what is m? M is 1 by vt. So 1 by vt is come forward. So is by vt e to the power vdq by vt is equal to idq by vt. Okay, simple. So now where we know the small signal resistance RD is nothing but, or the small signal equivalent is 1 over dou ID by dou VD. Okay, but at the operating point VDQ. So we can say dou ID by dou VD, the value of IDQ of VT, the reciprocal of this will be the RD. So RD will be VT by IDQ. So small signal resistance of diode is VT by IDQ. So the first derivative gives us the incremental resistance. Okay, and incremental conductance, and inverse of that conductance becomes the small signal resistance of the diode. So now the diode can be replaced by a DC bias component plus a small linear resistor for incremental analysis. This is the true origin of the diode small signal model. Okay, or the diode small signal resistance. You always see that RD is equal to VT by IDQ. Okay, So this is the thing. This is the RD is equal to VT by IDQ. So now finding constraint on small signal approximation. This is a very important thing. Now we analyze the validity region more carefully. If the signal swing becomes large, if the signal swings become large, higher order derivatives become important. Okay, and distortion starts appearing. So for every nonlinear device, we should perform this analysis at least once. Okay, to understand under what condition the small signal approximation remains valid. So this is very important for practical analog design because silicon does not care about our assumptions. The physics will always follow the full nonlinear equation. Okay, now let's see. This is IDQ, IS e to the power VDQ by VT. This is again this IDQ plus del ID IS e to the power something. Okay, now let's see. So this was your Is e to the power VDQ plus del VD by VT. Okay, easy. Now this is f of a plus h f prime a. So f of a is nothing but this thing Is e to the power VDQ by VT. So this was a. So f of a is Is e to the power VDQ by VT. Easy. Now h f prime of a. So we have to differentiate this IDQ and then we have to put this value. So del VD Is by VT e to the power VDQ by VT. Okay. Then h square divided by 2 factorial from the Taylor series formula. Okay. So this is del VD square by 2. 2 factorial is equal to 2. Now we'll differentiate again this thing. So again 1 by VT will come forward. So 1 by VT by Is by VT, 1 by VT square. So Is by VT square e to the power VDQ by VT plus dot dot dot. So we got this thing. Now this is equation 2, this is equation 1. Now by 2 minus 1 del ID is equal to del VD Is by VT e to the power VDQ by VT plus del VD square by 2 Is by VT square e to the power VDQ by VT. So this is the whole thing. Now if I have to, for valid signal approximation, this term should be greater than this term. Okay, if del VD is small enough, this term will be greater than this one. Okay, so for valid small signal approximation, this term will be greater than this one. So now this is is cross, this goes vanish, this VT goes vanish, there is a one VT, this VD goes vanish, there is one VD, and this thing e to the power VDQ by VT e to the power VDQ by VT, that also goes vanish. So del VD is less than twice times of VT. So what is VT? VT is nothing but 26 millivolt at 300 Kelvin. Okay, so del VD is less than 52 millivolt. So what does it mean? It means that your small signal V in should be such that your del VD can cross this 52 millivolt. It will be less than 52 millivolt for valid small signal approximation. And for any kind of nonlinearities, we should redo this whole analysis at least once to understand under what condition the small signal approximation hold. Okay. So standard way to work out for quotient and incremental analysis. Uh, okay. So now we can summarize the standard engineering workflow for small signal analysis. So step 1, find the DC operating point or quotient point. Step 2, replace the nonlinear device with its incremental equivalent around that operating point. Step 3, perform linear incremental analysis. Okay, so these are all the steps. Now step 4, add the DC solution and incremental solution together to obtain the total response. Okay, now notice something important. If the signal amplitude change significantly, incremental analysis must be redone. Okay, but the DC operating point analysis usually remains unchanged unless the bias changes. This is why designers separate DC analysis and AC small signal analysis. Okay, and finally, so now we finally have the mathematical framework for linearizing a one port nonlinear device. And in the next lecture, we will extend this exact same framework to two port systems, and finally we will derive the MOSFET small signal model completely from scratch. including channel length modulation. That is where the real amplifier model will finally emerge. So thank you everyone. See you in lecture